so what we're doing today is the conjugate root theorem. And we might get into the fundamental theorem of algebra. We'll see how that goes. But for now, we are doing the conjugate root theorem. Now, not as important to you, but I do want to talk about when this actually applies. First of all, it applies when we are doing polynomials. It applies when we're talking about factors and roots. And there's something specific about our polynomials that has to be true. It has to be that all the coefficients are integers. Okay, we need to have integer coefficients. We aren't going to have like anything weird going on.
No fractions?
Well, I haven't seen an example with a fraction. I'm pretty sure it has to be integer coefficients, which is every single example that your textbook is giving you. Okay, so what is the conjugate root theorem? Well, basically says if one conjugate is a root or factor, then the other one is too. So that's either going to make this really easier for us or harder for us. It really depends upon the question that's being asked. So, for example, we could write a polynomial. So this is going to be the question like we had before. Write the polynomial with the given roots. Well, let's say my roots are root 5 and root 7. Well, because of the conjugate root theorem, that means without it being stated, you need to know I also have negative root 5 and negative root 7. Okay, without it being stated. So our function, p of x, is going to be x plus root 5, x minus root 5. I'm running out of space here, but then the next one would be x minus root 7 and x plus root 7. See, I have the conjugates. I have all of them. Okay? So if I have one conjugate, I have the other conjugate. Okay, so let's say I have same question, write the polynomial. So you don't need to with the given roots. I could have x equals 2 minus 3i and x equals 8. Okay, so that's what I'm given. Because of the conjugate root theorem, I know I have also x equals 2 plus 3i. You with me? Now the common error is to come over here and look at this 8 and say, oh, x equals negative 8. But conjugates only apply to radicals and complex numbers. So that's not true. Don't fall for that trap. That's a trap. Do not fall for it. The conjugate root theorem is going to apply for radicals and complex numbers. It does not apply just to this, okay? It didn't before and it doesn't now. Okay, so I have these roots. So I have x equals 2 minus 3i, I have x equals 2 plus 3i, and I have x equals 8. And I'm going to write the polynomial. This time I'm going to multiply it out to get it in standard form. So I need to get everything to the left, right? So I'm going to subtract 2, and I'm going to add the 3i to both sides. I'm going to subtract the 2 and subtract that 3i, and I'm going to subtract the 8. So I get x minus 2 plus 3i is my factor, and I get x minus 2 minus 3i is my other factor, and I get x minus 8. Any questions on how I get all my factors? So f of x equals that stuff. Now the tricky part, I am going to multiply. Now it does multiply the way you normally would, I just have i's, and we need to remember, now I put an x here, that should have been an I right there. Remember, and some of you forgot this on your last test, you need to remember I squared equals what? Negative 1. And we get an I squared whenever we do I times I. We get negative 1. Okay? I squared is negative 1. We need to remember that. So I'm going to multiply these out. X times x is what? X squared. Now notice, I'm not going to start multiplying over here. I'm going to start with my conjugates. Okay? And then x times this is going to be negative 2x. And then finally, that's a 3i. I just messed it up. That's going to be minus 3ix. I'm just going to put the x last because of Mr. Keynism. Okay, now I'm going to do the negative 2. Goes to everything. So I get negative 2x plus 4 plus 6i. Any questions on how I got that? I squared, thank you. Yes, I times I is I. Wait, whoa. It's just negative 2. There's no I on that. Negative 2 times negative 3 is positive 6, and I have 9.
You haven't done the 3i then.
I haven't done the 3i yet. Okay, so now we're going to do the 3i. 3i times x is plus 3ix. Now 3i times negative 2 is negative 6i. And then 3i times negative 3i is negative 9i squared. So there is a lot of room for it. Now I haven't even, see, I'm at risk to forget this part. I can't drop it. I just want to simplify this multiplication here because I'm going to get a mess here pretty quick. Alright, so let's simplify that down. I get x squared, nothing's like that x squared. Let's see here, negative 2x. Do I have any other x terms? Right here. That's it. So minus 4x. Okay. Let's look at for negative 3i. Negative 6i. That's negative 3ix. Do I have another 3ix? Right here. Right? So those cancel out, don't they? So I have none of those. Okay, I'll hold on to that 4. Anything like 6i? Yeah, minus 6i. So those goes away, don't they? And then 4, now what's this? Well, that's going to be 9 because I squared is negative 1. So I have 9 plus 4 is 13. And now I need to remember this x minus 8. Now, notice what happens. All the i's are gone. Okay, that's important. Alright, x squared times x cubed. X squared times negative 8. So I brought down this. I don't want to forget that. Then minus 4x squared plus 32x plus 13x minus 104. Is that correct? And then finally I simplify that. X cubed minus 12x squared plus 45x minus 104. All right. Hopefully I multiplied right there. Well, maybe I didn't. I think I did. I think I'm good. Okay. All right, so let's do one with radicals. Actually, let's do one with radicals and imaginary. Okay? So we're going to, same question, write a polynomial with the given roots. Let's say that the first one is negative 3i. And let's say the other one is x equals root 5. Because of the conjugate root theorem, I know that I'm also going to have x equals what? And also x equals negative root 5. Okay? Because of the conjugate root theorem. So my polynomial is, well, before I get to there. So I'm going to line all these up. X equals negative 3i, x equals 3i, x equals root 5, x equals negative root 5. Notice how I put the conjugates right next to each other? I mean, it's not required, but it's going to make your life a lot easier. So then do you see that my factors are then x plus 3i, x minus 3i, x minus root 5, x plus root 5. Do you see that? Any questions on how I got those factors? See the difference between a root and a factor? I mean, we get our roots from the factors, and vice versa, but they are different. The factors I'm going to multiply. So my p of x, I'm going to multiply those two conjugates together and these two conjugates. Is it wrong to do it different? No. But boy, will you get a very big mess if you don't multiply the conjugates together right away. Okay? Because I'm hoping my i's cancel, and I'm hoping my radicals cancel. That's what should happen. So when I multiply those two, notice I'm putting my answer in parentheses. I'm going to get x squared minus 3ix plus 3ix minus 9i squared. Any questions on how I got that from my multiplication? The next one, x squared plus root 5x minus root 5x minus root 25. I'm just going to simplify that a little before I multiply on. Notice those cancel, don't they? And then I squared is negative 1, making this x squared plus 9. Notice those cancel. And what's the square root of 25? So I get x squared minus 5. Now I can multiply this. X squared times x squared is x to the 4th minus 5x squared plus 9x squared minus 45. P of x. Simplify. Boom. Okay, so that's our polynomial multiplied out. Now sometimes I'll say to you, because I don't necessarily want to, I definitely want you to make note of, no matter what, the factored form. Okay, this factored form up here. If you can make note of that, I know that you understand, and that if you don't get this exactly, it means you have a multiplication error. Okay? So make sure you've made note of that factored form. Any questions on using the conjugate root theorem?
Can you use just for polynomials?
Huh?
Can you use just for polynomials?
Yes. Okay? Which is this entire chapter is that concept. Okay. Next thing. Rational root theorem. I introduced this last time, but the rational root theorem is going to start with the same premise as the conjugate root theorem. It's going to apply to polynomials, and it has to have ones with integer coefficients. Okay? The rational root theorem is going to give me my possible roots to test. And what this is going to say is that the possibles are the factors of the last term over the factors of the first term. Those are the ones that I could test. And sometimes in your book, in your homework for this section, all you're asked to do is list the possibles. You don't even have to do anything except list them. So let's say, for example, I give you f of x equals 2x cubed plus x squared minus 7x minus 6. And I want to know, well, what are the possible roots? What are my possibles? I'm going to use the rational root theorem, which says that it's the factors of the last over the factors of the first. Well, what do I mean? The last term is negative 6. The first term is 2. So the factors of 6 are 1, 2, 3, and 6. Plus or minus, right? Lots of combinations there. And the factors of 2 are plus or minus 1 and plus or minus 2. So now what I need to do is get all the combinations. I want you to watch how I get these combinations. So here's how I start. 1 over 1 plus or minus 1. 1 over 2 I'll do later. 2 over 1 plus or minus 2. 3 over 1 plus or minus 3. 6 over 1 plus or minus 6. Now I'll go back. 1 over 2, that's a half, right? 2 over 2 is simply a 1, and I already have that. You see what I'm saying? 3 over 2, and 6 over 2, well, what's 6 over 2? 3, and I already have that. Those are my possibles. So if I were trying to factor, I would use these in my synthetic division. These would be the only ones that I'd test. 1 or negative 1, 2 or negative 2, 3 or negative 3. And we can use our calculator to figure out which one I should actually test, right? Wherever it crosses the x-axis, our roots, except if we're imaginary, our roots cross the x-axis. We'll do one more example of listing the possible roots. And then what I want to end class with is actually an example of factoring one of these and finding all the roots. Okay. One more example of listing the possibles. For listing the possibles, notice none of the middle stuff matters. Only the last and first term. What do I mean last and first term? You have to make sure you have them in order. First term, last term. So my possibles. What are my factors of 2? Plus or minus 1, plus or minus 2. What are my factors of 15? Plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So now I need to get my combinations. 1 over 1, 2 over 1. So, plus or minus 1, plus or minus 2. Do you see how I got that? Now, 1 over 3, 1/3. 2 over 3, 2/3. Now, 1 over 5, plus or minus 1/5. 2 over 5.
Wait, how do you do that? Oh.
So I'm basically saying boom, 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 boom.
No,
Then the same thing with a 2. But the pattern I'm doing is I do both the numerators to the first denominator, both numerators to the second denominator, both numerators to... Whatever pattern makes sense to you to get all the combinations, but in essence you need to pair each of these up with all the denominators. Does that make sense? So I'm doing this as a group over 1, this is a group over 3, this is a group over 5, so now this is a group over 15. That's going to be plus or minus 1/15 and plus or minus 2/15. These are my possibles. And legit, some of the questions, that's all I asked you is get the possibles. You don't even have to do anything else. But it's getting all those combinations that will be the trick. All right, the last thing for today is going to be getting, I want you to factor and find all the roots. We'll probably do 2 examples of this. Okay. So this is going to get to my fundamental theorem of algebra, which we'll talk more about tomorrow. But look at this 4. That means 4 roots. Okay? Now, they might not all be real. Remember when we started this chapter, we said up to 4 roots. We should have said there are 4 roots. It doesn't matter whether they're real or not. So we should have said up to 4 real roots. If we don't have 4 roots, then that means the others are imaginary. So 4 roots. Now, if there's imaginary, that means there's 2 of them. Okay, that would be imaginary. Okay, so first thing I'm going to do to find all the roots are list my possibles, because I don't want to waste my time. So my possibles, factors of the last term over factors of the first term. So that's plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15, all over the factors of the first term, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now I'm going to want to eliminate my repeats. So 1 over 1, plus or minus 1, 3 over 1, 5 over 1, 15 over 1. Okay? Now, 1 over 2, 1 over 3, 1 over 6. Now I'll do 3 over the rest of them. I don't know why I changed my pattern. I just didn't change my pattern. Plus or minus 3 halves. Now 3 over 3 is 1, so I don't need that one. And 3 over 6 is a half. Now I'll do 5. Yep, there's a lot of them. 5 over 2. 5 over 3. 5 over 6. Now I'll do 15. 15 over 2. 15 over 3, which is just 5, so I don't need that one. And 15 over 6. Does that reduce? 15 over 6. Divide by 3. 5 halves, which I already have, so I don't need that one. So these are all the possibles. So these are all the ones that I would test in my synthetic division. Because Mr. Kane's a cheaty face and looking at the answer, I mean, you really would. That's why I say write your synthetic division in pen and then use a pencil to do all your testing. But I'm going to tell you by looking at the answer, that's the one I'm going to want to test, and that's the one I'm going to want to test. Okay?
Test for what?
Well, with our synthetic division, because when I divide synthetically, if my remainder is 0, that means it's a factor, which means it's a root. Or it's a root, which means it's a factor. Okay? Remember we set this up when we said if our remainder is 0, it's a root. Okay, so 1/3 and 1/5. So I'm going to go to the next page. I'm going to test 1/3 and 1/5. And I am going to, I'm going to grab this Okay? I'm going to grab this, because that's my polynomial. Okay, I'm going to paste that. There's my polynomial. What was that? F of x? Was it f of x equals? I want to make sure I didn't miss a negative. Yep, it was equals. Okay, so remember I set up my synthetic division. 6, negative 13, 13, negative 39. Remember doing this? Negative 15. And if we get 0, that means we have a root. Now, it's plus or minus, so I'm going to have to test for a negative and positive. Let's test the negative 1/3. See if that's one of them. So we have 6. What's 1/3 times 6? Add down, negative 15. What's negative 1/3 times 15? Positive 5. And negative times negative, positive. Add down, I get 18. You could have a bunch of fractions in here, that's possible. Negative 1/3 times 18. Negative 6. 18 times negative 1/3 is negative 6, right? Cancel. Negative 6. Add down. Negative 45. What's negative 1/3 times negative 45? Positive 15. Now when I add down here, I get a 0. That means this is, look, that means this is, remember doing this? That is a root, which means 3x plus 1 is a factor. You get what I'm saying? Sometimes you're asked to factor it, and sometimes you're asked to solve it. Right now we're going to solve, so we have one of them. Now, I don't want to go back up to this whole thing to test the next one. You with me? I've already divided one out. I'm going to want to use this piece. Okay? Because I'm getting it down one piece at a time. Alright, so by inspection and looking at the answer or looking at your calculator, I know that 1/5 is a possibility. But the question is, which one? Or not 1/5, it should have been 2/5. Or 5 over 2, yeah. So the question is, which one? Well, let's just take a risk. Let's try the negative 5/2. Now I'm going to use this piece right here. Ignore that 0. 45, make sure I copy it right. So, negative 5/2, 6. I'm going to want my calculator handy to do 5/2 times 6. It is going to be 15, right? Negative 15. Okay, negative 30. 15 times 5. Negative. And then at this point I can see, like, there's no way I'm going to get a 0 here. So I'm not going to waste my time. I see right away that that's not going to work out. So I'm going to do positive 5/2. See if that works out. So 6. And now I get 15, which gives me a 0 right there. That's what's going to help me out. So I get an 18 right here. And then 18 times 5/2, the 2 cancel, so I get 9, and 9 times 5 is 45, and then I get a 0 right here. Okay? So that means x equals 5/2 is a root, which means 2x minus 5 is the factor. Do you see how I'm getting my factors? Now, I don't want to divide this synthetically. Well, why not? Well, because I'm down to a quadratic. 6x squared, 0x plus 18. At this step, I could factor out a 6 and get x squared plus 3. Do you see where I got that? How did I know that it was x squared? Because I've divided how many times? Twice, which means this power has decreased down to a 2. Okay, because I've divided twice. So now, at this step, I could use the quadratic formula is what I'm going for there. Okay, so let's quadratic formula that. So we're going to go to the next slide. So far I have x equals negative 1/3. I have x equals 5/2. I'm trying to get the last two. I have this x squared plus 3. So what's A? 1. What's B? B is not 3. B is the number in front of the x term. There's no x term, so B is 0, and C is 3. So I'm going to use quadratic. Negative B is 0, plus or minus square root B squared, 0, minus 4 times A times C, all over 2A. So I get 0 plus or minus square root of negative 12, all over 2. Do you remember how to deal with that negative 12? I put an I instead of the negative, but I'm not even done yet. That root 12 can simplify to 2 squared times 3. The square root of 2 squared is 2, so 2 root 3. With an I. Oops. And then we get root 3i, plus or minus. So what are my roots? X equals negative 1/3, x equals 5/2, and negative root 3i, and positive root 3i. Whew. Done.